So let's look at this Maclaurin series. Consider continuous function f, which can be differentiated infinitely many times. The Maclaurin series expansion of f of x is f of 0 plus x f prime of 0 plus x squared over 2 factorial multiplied by f double prime of 0 plus x to the 3 over 3 factorial f triple prime of 0, and then so on and so on. Nth degree Maclaurin polynomial approximation to the function f is n starts at 0, infinite terms, and the function is f to the nth degree, or f to the nth derivative of 0, x to the n divided by n factorial. So what this all means is that the Maclaurin series just allows us to express a function in terms of a power series. What that basically means is, like, you can express a function, any function that converges to a specific number as a polynomial like this, a polynomial with infinite terms. So let's do some examples of how to find the Maclaurin series of different functions. So number one, we have find the first three terms of the Maclaurin series of the function f of x equals cosine x. So if we remember, the Maclaurin series of f of x is equal to f of 0 plus x f prime of 0 plus x f prime x squared over 2 factorial f double prime of 0, and so on. So all we have to do is find these three terms. So f of 0, or let's just say f of x is equal to cosine x. So f of 0 is equal to cosine 0, which is equal to 1. Next, we have to find the derivative of f of x. So f prime of x is equal to negative sine x. So f prime of 0 is equal to negative sine, or sine 0 is 0, so negative sine 0 is still 0. And then f double prime of x is equal to negative cosine x. So f double prime of 0 is equal to, we know cosine 0 is 1, so negative cosine 0 is negative, or let's just say negative cosine 0 is equal to negative 1. Okay, now that we have these three values here, all we have to do is just plug it into the equation. So let's just draw an arrow here. So f of x is equal to f of 0, which is 1, plus x times f prime of 0, which is 0, plus x squared over 2 factorial multiplied by f double prime of 0, which is negative 1. So this is going to turn out to be 1 minus x squared over 2 factorial. Now we need to find one more term, because that's what the question says. Find the first three terms, but we only have the first two terms. So all we have to do is just find the third factorial, which is going to be f triple prime of x is equal to negative cosine x is negative sine x, so negative cosine x is just sine x. So f triple prime of 0 is equal to 0. But what we see here is that we get 0 again, and that's not going to give us another term. So once again, we have to find the fourth factorial. So f of 4 of x is equal to cosine x, and that's the exact same as x, or f of x. So of 0 is equal to 1. So now, what would have been with 0 here is x to the 3 over 3 factorial. So this is going to be x to the 4 plus x to the 4 over 4 factorial multiplied by 1. So we're just going to leave it at this. So these are the first three terms of the Maclaurin series of cosine x. Now what else we can do with this is find the power series, or the sigma notation for this function. So we're going to have our sigma, n is equal to 0. That's our first term. And we're going to have infinite terms. And now we need to find the function here. And to do that, we just have to look at this and recognize patterns. One thing I like to do when I'm trying to find the sigma notation for a function is I try to make every single term, or which is usually just the first three terms, in the same format. So you see how the second term and the third term are the same format. We have x to a power divided by something factorial, x to the power divided by something factorial. Here, we don't have that, but we can set it equal to something. So if we just go over here, let's go here. 1 is equal to x to the 0 divided by 0 factorial. This is equal to 1 because x to 0 is 1 and 0 factorial is also 1. So 1 over 1 is just 1. But what we did here is we manipulated the first term in order to be the same format as the second and third term. Now it's a lot simpler to find the sigma notation for the function, because we see that there's two requirements we have. We have to have x to the something power divided by 0, or not 0, something factorial. And that's true for all remaining terms, including the first three terms. So all we have to do is x to the n divided by n factorial, but this is not our final answer. You see how our numbers, or our exponents, are increasing by increments of 2. The next term is going to be x to 6, and then 8, 10, 12, and so on. So we're going to put a 2 on here to represent that increase of 2. And it works because if you put n equals 0, you're going to have x to the 0, which is just 1. And if you have, and by the way, this first term is actually, in terms of the power series, the 0th term. This is actually the first, and then this is the second. And then we have to do the same thing for the factorial as well. We're going to have to do 2n factorial. And that works again because if you put n equals 0, which is the first term, it's going to be 2 times 0, which is 0 factorial. If you put n equals 1, we'll have 2 times 1, which is 2 factorial, and it's 2 times 2 factorial. But we're still not done. You see how this function swaps from being negative to positive? If you keep going, the next function is going to be negative. The next term is going to be negative, and then positive, and then negative, and then positive. So to get that, all we have to do is multiply the entire thing by negative 1 to the power n. And once again, this works because if you set n equals 0, negative 1 to the 0 is 1, which is positive, and that represents this first term here being positive. N equals 1. This term is going to be negative because negative 1 to the 1 is negative 1. So negative, and then n is 2, positive, n is 3, negative, 4, positive, and so on. So this is our power series for the function. And then this is the first three terms of cosine x. Question 2, we have, find the first three terms of the Maclaurin series of the function f of x equals e to the x. So we're going to use the same method as we did with the first one, which is cosine x. So once again, f of x is equal to f of 0 plus x f prime of 0 plus x squared over 2 factorial f double prime of 0, and so on. So once again, f of 0, f of x is equal to e to the x. F of 0, e to the 0 is 1. And f prime of x, so the derivative of e to the x is e to the x. So f prime of 0 is 1. And the same thing is going to be for the second derivative as well. Equals 1. Now all we have to do is plug it back into the Maclaurin series. So we'll draw another arrow here. F of x is equal to f of 0, which is 1, plus x times 1 plus x squared over 2 factorial times 1, and so on. All we need is the first three terms. So now let's find the power series for it. So sigma n is equal to 0, infinite terms. And once again, actually let's clean this up a little. So this is just going to be 1 plus x squared over 2 factorial, and so on. So these are the first three terms. And now to find the power series for this, let's make each term the same format. So 1 is equal to x to the 0 divided by 0 factorial. And the reason I'm using 0 and 0 here is I noticed a pattern in the exponent and the denominator. I see that this is x squared and this is x to the 1, so this must be x to the 0. Same thing with the denominator with the factorial. This is 2 factorial, and this has to be 1 factorial, and this has to be 0 factorial. And the thing is, 0 factorial is the same as 1 factorial because they're both equal to 1, which is why you don't see a denominator for the first and second term. So that's why I wrote it in this format, and we'll do the same thing for x. So x is equal to x to the 1 over 1 factorial. Now we have the format for every single term in the Maclaurin series. It's going to be x to something divided by something factorial. The same as cosine x, but the exponent and factorials are a little different. So this is just going to be very simple. X to the n over and factorial, and that's it. Because if you see here, the 0th term in terms of the power series, if you plug in n equals 0, x to the 0 is 1, divided by 0 factorial, still 1. And if you put n equals 1, which is going to be x to the 1 over 1 factorial, which is x, n equals 2, x squared over 2 factorial, third term, and so on. So this works, and these are our two final answers. This is the power series, and these are the first three terms. Question 3, we have, find the first three terms of the Maclaurin series of the function f of x equals x cosine of 2x. So once again, we have just the Maclaurin series of the function, and this is something you should just have memorized by this time while you're doing these problems, just so you don't have to go through the hassle of figuring out what this is. And if you just have memorized, you can just quickly write it down and you know what the template is, just to find however many terms you need to find for the Maclaurin series, or whatever function you're gonna need to find. So for this problem, we're gonna have to do something different, but let's try the same approach we've been doing for problems 1 and 2, which is finding the derivative, and then the second derivative, and the third derivative, and so on. So first we need to find f of 0. So f of x is x cosine of 2x. So f of 0 is 0. And the first derivative is, now we're going to have to use product rule because we have x multiplied by another function, or another function multiplied by another function. So we're going to need to use product rule for that. But technically you could do that for finding however many derivatives you need to find, and then plugging all the values into the Maclaurin series, and then finding the first three terms. But if you see, for just the first derivative, we need to find the product rule. For a second, we need to find the product rule again, and then again, and again, again. And it's going to eventually become very messy and very complex to handle. Technically, you could still do it, but there's a lot more ways that you could make errors, find the derivative wrong, or like you make a calculation error. It's very easy to mess up doing product rule that many times. And there's a much easier approach to doing this. So what we can do instead of finding the derivatives is we can use a parent function of x cosine of 2x. Or we can just use a parent function of cosine of 2x, which is just cosine of x. And we found the first three terms of cosine x already. So f of x equals cosine x is equal to 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial. Now we can just keep adding on to this, manipulating this function to get this without having to do any derivatives whatsoever. So first, let's make the angle 2x instead of x. So f of 2x equals cosine 2x equals 1 minus 2x squared is 4x squared over 2 factorial plus 2x to the 4 is 16x to the 4 over 4 factorial. Now we need to just multiply by x. So f of 2x is equal to x cosine of 2x equals, now we just multiply every term by x. So x minus 4x cubed over 2 factorial plus 16x to the 5 over 4 factorial. And now we already have our first three terms. And in fact, in my opinion, that was a lot more simpler than finding the derivatives for each term and then plugging in and then simplifying. So if you have a function that's branching off of the parent function, you can go back to the original and keep adding on until you get to the function that they want you to find the first three terms of. And you can use same methods that we did here. And now we can find the power series for this now. So let's write x in terms of these two functions, or of these two terms here. So x is equal to, and I see here that the exponents is differing by 2. So 5 minus 3, or 5 minus 2 is 3. So 3 minus 2 is 1. So x to the 1 divided by, and in the denominator with the factorials, I see that 4 factorial and 2 factorial, 4 and 2 is the difference of 2. So 4 minus 2 is 2. 2 minus 2 is 0. So 0 factorial. And there's also a 4 this time. So we have to multiply 4 to the power of, in this case, this is 4 to the power 1. This is 4 to the power 2. So 2, and then 1, and then 0. So this is 4 to the 0. And we're still not done. The signs are swapping again. So it starts from positive to negative, and we figured out that before, and this is going to be negative 1 to the 0, because negative 1 to 0 is positive 1. So now every term is in the same format. Now let's find the power series of this function. So n is equal to 0, infinite terms, and then this is the format that we're going to have to go off of. So let's write negative 1 to the n first, and then this is going to be x to the, this is going to be, first we know that the powers are swapping, or the increments is by 2. So we'll write 2n, but that's not it. Since these are odd powers, we're going to have to do 2n plus 1. And this works because if you put n equals 0, this is going to be 2 times 0, which is 0, and then plus 1, which is just 1, x to the 1, x to the 1. n equals 1, 2 plus 1 is 3, x to the 3. And then 4, now we're going to have to include the 4 here. So 4, this is just going to be 4 to the n. And then, because you see here, this is 4 to the 0, 4 to the 1, 4 to 2, and then 3, 4, 5, 6, whatever. And the denominator is just going to be 2n factorial. Because you see here, this is 2 times 0, 2 times 1, 2 times 2, and then so on. So this is the final power series for x cosine of 2x. And these right here are the first three terms. Question 4, we have, find the first three terms of the Maclaurin series of the function f of x equals e to the x squared. So we're going to have to use the same method that we used for question 3. So we're not going to find the derivatives at all. So f of x equals e to the x. And all we have to do, first, we know that e to the x is 1 plus x squared over 2 factorial, and so on. So all we have to do to get e to the x squared is set x as x squared here. So f of x squared equals e to the x squared equals 1 plus x squared plus x to the 4 over 2 factorial, and so on. And to find the power series, well, first let's box in the first three terms. To find the power series First, let's set 1 and x squared as the same format as this. 1 is equal to x to the, and we see the exponents are decreasing by 2, so 4 minus 2 is 2. 2 minus 2 is 0, divided by this is 2 factorial, 1 factorial, and 0 factorial. So 0 factorial, and x squared is equal to x squared over 1 factorial. Now all the terms are in the same format. So the power series, n is equal to 0, infinite terms. So all we have to do is find, we have two requirements, x to the something divided by something factorial. So x to the, this is going to be 2n divided by n factorial, because this is, the exponents are increasing by 2, and it's only 2n because it's even terms. So this is the 0th term, the second term, 0th exponent, second exponent, and x to the 4. And the signs aren't switching, so there's no -1 to the n. So these are our final answers.